Okay, ladies and gentlemen, this is the video on bond enthalpy. All the notes that are in this video are coming straight from the PowerPoint slides, from the very last slides from the Chapter 8 notes that are posted online. In the practice problem, it's the exact same practice problem, but we're just going to be solving that. Again, you can read about bond enthalpy in the book or watch this video, but in terms of class time, we can talk about other stuff instead. Bond enthalpy. Bond enthalpy, which is sometimes abbreviated as D, capital D, I know this is kind of a funny abbreviation, is the energy required to break a covalent bond. We already talked about how this is always going to be positive, meaning it's always endothermic. It will always take energy to break a bond. Always, always, always. Because the whole reason that things bond is to become more stable. So if you're talking about taking things that are stable and upsetting the balance, that's going to require some energy to do that. You're taking stable things and you're making them unstable. That will require energy. An example of bond enthalpy is this reaction that's shown right here. Cl2 gas goes to 2 chlorines, meaning you are breaking the bond between the 2 chlorine atoms, and now you're completely separating the chlorine atoms from one another. And the delta H, this is an enthalpy, so this is delta H. Sometimes it's shown as dCl-Cl, 242 kilojoules. And I will note that this dash right here is meant to represent the single bond between the chlorine atoms. So this is saying that the chlorine, in order to break the single bond between the 2 chlorine atoms that is in Cl2, you will need to put in 242 kilojoules of energy. When you're considering the reaction, say a reaction where you are breaking more than one bond, as in this case right here, if we have a look at this right here. The CH4 gas goes to C gas plus 4H gas, meaning CH4 carbon and 4 H's, there are 4 carbon to hydrogen single bonds. This reaction shown again right here, CH4 gas goes to C gas plus 4H gas. This whole thing has an overall enthalpy of 1660 kilojoules. This is for breaking 4 carbon to hydrogen bonds. So that's how much energy is required total to break 4 carbon to hydrogen bonds. Well, then how much energy is required to just break 1 carbon to hydrogen bond? Take an average, right? This value right here is for 4 CHs, so shown right here. Just one C to H bond is only going to be a quarter of that amount. So 1660 divided by 4, 415 kilojoules is the average for breaking 1 carbon to hydrogen single bond. So if we're in a case where we have multiple bonds being broken, often bond enthalpy is calculated by simply averaging the entire atomization event. Now, utilizing bond enthalpy. Bond enthalpy, as you can probably imagine, is yet another way that we can calculate overall enthalpy for a reaction. It's that whole state function thing. We have more than one way to determine state functions. That's what state function means. Enthalpy is a state function. So we can use the bond energy information, how much energy is required to break a bond, in order to figure out the overall enthalpy change in a reaction. Essentially, what we do to figure this out, we add up the energy it took to break the bonds that we're breaking. You look at your reaction and you think, okay, what bonds in this reaction are we breaking? Add up those energies. Do the same for the bonds that we're forming. But because we're forming bonds is exothermic. So we are going to subtract the energy we get from forming bonds. Meaning, how much energy did it take to break the bonds that we're breaking? How much energy will we get from forming the bonds that we're forming? Combine the two, we can get delta H. So put another way, it's bonds broken minus bonds formed. Bonds broken minus formed. And remember, this is the sigma, that means the sum. So you add up all of the bond energies. Remember, D is bond energy. You add up all the bond energies for the bonds that you're breaking. These are endothermic. right? This is energy that has to go in. You want to break these bonds, you have to input that energy. But you're also going to be forming some bonds. This is exothermic, hence the minus. This is why it's minus. Broken minus formed. So how much energy do you need to put in versus how much energy will you get out? The difference between the two is the overall enthalpy of the reaction. In order to determine which bonds are broken and which bonds are formed, you need to draw things. You need to draw the structural formulas for the element, for the molecules involved in the reaction, and then look at it, actually look at it and say, okay, well, this was a bond that we started with, but we don't end with. That must mean we're breaking it. This is a bond that we end with, but we don't start with it. So that must mean we are forming it. It is bonds broken minus bonds formed. And I will add that this formula is not on your reference table. This is something that you have to remember. But if you can sort of keep in mind that, okay, how much energy does it take to break the bonds? That's endothermic. How much energy will it take to form the new bonds that we're making? That's exothermic. Add them together. The negative will mean exothermic. And you can remember this. So we're going to do a practice problem so you see how this works. Find the energy for the reaction from D. Again, D is bond enthalpy. So this is saying using bond enthalpy information. And we have a reaction written right here, and we have a table of bond enthalpies right here. These are things that you will be supplied with. So we've got the reaction written out. We need to figure out delta H. We need to figure out the energy for this reaction. You have to draw. So we're going to draw everything out. So I'm going to draw all the reactants and all the products so that we can look at their bonds. Reactants. I will label them as such. So on the reactant side, we have 2, and I'm going to put that in front, 2, and it says CH2. Well, okay, what is that in terms of bonding? That's a carbon, single bond to 2 hydrogens. What comes next in the formula? Oh, we've got that double bond, so let's draw that double bond next. Then it says CH. We're up to here in that reactant. So I've got a C, single bonded, and it's connected to an H, right? It says CH, so there's an H coming off of that C. And then I've got CH3, so H, H, H. There we go. That's one of the reactants. Then I've got NH3. That's pretty easy to draw. I can draw that. Straightforward, 2 of those. And then O2. That's O2. There we go. So these are my reactants. Now we're going to do the same thing. We're going to draw the products. Going to draw the products. So anytime Smartboard is having a moment. It's not having a dipole moment. It's just having a regular old moment. Okay, so we're going to draw the products now. Products, we've got, again, looking back at this thing that was written, 2CH2 double bond CH, triple bond N. So we're just going to draw that out, and you just take it one at a time. That first carbon is attached to 2 hydrogens. Then, if we go back and have a look, it's double bonded to another carbon. Okay, so we just draw the double bond carbon, and then it's attached to a hydrogen. Then have a look again. Then it says C triple bond N, that last component right there. So, all right, C triple bond N. And then what else do we have? It also says 6 waters. You go back, have a look. 6H2O. Okay, so 6H2O. We know what water looks like. That's easy. We can draw that. So we've got our reactants, we've got our products drawn out. Reactants are about breaking bonds. Products are about forming bonds. So now let's compare the two. What are the bonds that are different? You could simply assume that you're going to break absolutely all of the bonds in the reactants and you're going to form absolutely all the bonds in the products. You could do that and do that math and get the correct answer. However, that's not the way chemistry works. You don't break all the bonds in the reactants and form all the bonds in the products. You only break certain bonds and you only form certain bonds. as you can see, there are some bonds that are the same. For example, if you have a look at this section right here, this C with two H's and then double bond C and then then an H and then a single bond to a C. Look, this is identical to this section of the product. That means that all those bonds that are there, we're not breaking any of those bonds and we're not forming any of those bonds. Those bonds are all staying exactly the same. These sections are the same. However, things get different when you look at the end, because look, right here, this is a bond that was formed, meaning it's a product, but we didn't start with it. And where is it coming from on the reactant side? It's coming from the breaking of these bonds. Those three carbon to hydrogen single bonds had to be broken in order to form the carbon to nitrogen triple bond. So this is a new bond. The carbon to nitrogen triple bond is a new bond from what we started with. In order to make that, we had to break the three C to H bonds that are at the end of that thing, that reactant. And then similarly, we look at the other reactants. We start with this ammonia, with this NH3, with these three N to H single bonds. Look at our products. We don't have any N to H single bonds. That must mean we are breaking all of these. We're breaking all of these N to H single bonds. Ditto for this oxygen-oxygen double bond. We do not have an oxygen-oxygen double bond in our products. That means that O2 that we're starting with, we have to be breaking that. But again, looking at our products, what is if there's something else that we end with that we don't begin with, and it's this oxygen to hydrogen single bond, that O to H single bond. And if we're going for completion's sake, we are making that too. This is a formed bond. So we've established what bonds were broken and which bonds were formed. Now we can do our math, because the math, again, delta H, the sum of the bond energies for bonds that are broken, minus the sum of the energy for the bonds that are formed. So figuring out what we're breaking. If you look at what we're before we even go to that, I'm going to make a list. So we broke a carbon to hydrogen bond. If you look up on the bond enthalpies list, right here, bond enthalpies, we broke, let's see, this one, carbon to hydrogen single bond. That's 413 kilojoules. But the question becomes, how many times did we break that carbon to hydrogen single bond? So, okay, let's have a look at that. This is right here where we have broken that carbon to hydrogen single bond. So how many times are we breaking it? We're breaking it 1, 2, 3 times. And if you say 3 times and that's how many times you're breaking it, you're wrong. Because, yes, we break it 3 times, but oh, look, we have 2 of these things, 2 of these molecules, which means that we're breaking that C to H single bond 6 times. 6 times we're breaking that C to H single bond. We are also breaking the N to H bond. We're going to go back up to that bond enthalpies list. Actually, let's bring that down here, just so we can see it a little bit better. Okay, there we go. We have that N to H single bond, which, again, we have a look right there. That's the N to H single bond. That's 391 kilojoules per mole. How many times are we breaking that bond? We'll go back up and have a look. N to H. Here's the N to H single bond right here. We are breaking it 3 times in the molecule, but there are 2 ammonias, which means that we are breaking a total of 6 N to H single bonds. We are also breaking the O to O double bond, which is right there. So that's 495 kilojoules per mole. If we have a look, how many times are we breaking that? Oh, just once, right? The coefficient for that oxygen, it's just 1, so we're only breaking that 1 time. Formed, bonds that are formed. What is it that we're making? We are making a carbon triple bond nitrogen. Carbon triple bond nitrogen is right there. That's 891 kilojoules per mole. How many times are we making that bond? How many times are we forming that bond? Well, here it is. It's right here. But oh, look, coefficient of 2. That means that we're making this molecule twice. That means that we are forming this bond twice. We also said that we are making that O to H single bond right here in the water. Now, if we look at the water, in every water we are forming 2 oxygen to hydrogen single bonds, but we are making 6 waters. So we must be doing this 12 times. And the O to H single bond is 467 kilojoules, 467 kilojoules per mole. I will point out that, have a look, we're not using them here, but have a look at the C to C bond, single bond versus double bond. A C to C single bond versus a C to C double bond, it's not simply a doubling. It takes a different amount of energy because a single bond is not, basically in order to make a double bond, it's not a true doubling of a single bond. There's more involved that we're going to be learning about in chapter 9, that the orbitals that are involved in a double bond are not the same as, you haven't simply doubled the orbitals that are involved in a single bond. So it's not the same, it's not simply taking the CC bond and then doubling it to get the C double bond C bond enthalpy. They are different, so you have to make sure you're using the correct thing. Okay, so we figured out what we're breaking and what we're forming, and then we're just going to use that formula, bonds broken minus bonds formed. Just like delta H of formation, be careful with your math here. So broken minus formed. We said that we are breaking that C to H single bond. That's 413 kilojoules per mole, and we are breaking it 6 times. We are also breaking the N to H single bond. That is 391 kilojoules per mole, and we are breaking it 6 times. And the O to O double bond, and that is 495 kilojoules, and we're only doing that once. From that, we are subtracting the bonds that we are forming. We are forming the C to N triple bond. That is 891 kilojoules, and we are making it twice. And we are also forming the O to H single bond. That is 467 kilojoules, and we're forming that 12 times. We are simply doing this math. You are going to your calculator and you're adding things up. When I add up everything from in here, I'm not even trying to do this all at once. I don't do these things all at once. Too many opportunities to make mistakes. I get 5,319. This is how much energy is required to break the bonds. And then I have 7,386. This right here is the energy released by forming bonds. It includes the negative, the subtraction. Because this is essentially saying if I wanted to break all of the bonds that are formed, it would require 7,386 kilojoules to do that, positive 7,386. But if I want to form them instead, I flip the reaction around, I negate the sign, and it becomes a negative 7,386. So the overall delta H, it's simply adding these two things together, 5,319 plus a negative 7,386, or bonds broken minus bonds formed, 5,319 minus 7,386. And hopefully you're doing this math on your own to confirm that you get the same answer I do. When I do this, I get an answer of 2,067 kilojoules. This is the enthalpy for the overall reaction, overall enthalpy value. So bond enthalpy is another way that we can calculate the overall delta H for a reaction. Bonds broken minus bonds formed. Draw them out. Look at them and say, this is a bond that we started with that we did not end with. That means that it was formed. This is, I'm sorry, flip that around. That means it was broken. This is a bond that we end with, but we didn't start with it. That means that it had to be formed.